Good day and welcome back. This is part 5 of our video series on the cross product. So at this point, we've really introduced, all of the definitions and associated properties that we need for the two vector products, the dot and the cross product. What we are going to do with our remaining time is investigate kind of one more example, and then we are going to have a worksheet for you all to work through. And this would be kind of finishing up maybe the last, 25 or so minutes of our second day of class dealing with the cross product. So let's begin by investigating the example of find the angle between a diagonal of a cube and one of its edges. So the first thing that we need to do is we have a cube drawn here, is we somehow need to introduce some maybe coordinates. We need to embed this in a coordinate system so that we have something that we can work with. So that also means we need to think maybe about kind of the length of one of the sides. Now, regardless of the length of one of these sides, the angle between a diagonal and one of the edges is always going to be the same. So let's just go ahead for convenience and assume that the length of each side is length 1, the simplest possibility really. And let's go ahead and embed this in three-dimensional space where we'll think of, the origin as being here. So if we think of having our three-dimensional coordinate axes, to get to this point over to the right, we would go 1 in the y direction. And if we want to find the angle between a diagonal and an edge, we can pick any corner to start. I'm going to go ahead and just pick the origin for convenience, and we can have all position vectors. So the diagonal would be the vector going from the origin up to this back right corner. And I'm going to go ahead and just call this vector B. And then one of the edges, there's two possibilities, but let's go with this bottom edge. Let's call this A. So we can see immediately that A is going to be the vector 0, 1, 0. To get to the terminal point of B, we need to go, 1 in the y direction, back 1 in the x direction, and then up 1 in the z direction. So the coordinates of this back right corner would be -1 in the x direction, because we've gone backwards into the screen, 1 over in the y direction, 1 up with the z direction. So that indicates that the vector B would be given by the position vector -1, 1, 1. And if we want to find this desired angle between the two, we now know exactly how we can do that. We have a formula or a property of the dot product that tells us cosine of the angle between is A dotted with B divided by the magnitude of A times the magnitude of B. So we really just have three kind of key ingredients that we need to compute. So by some quick computations here, the magnitude of A is 0 squared plus 1 squared plus 0 squared, so 1. The magnitude of B is the square root of 1 squared plus 1 squared plus 1 squared, which is the square root of 3. Additionally, A dotted with B is going to be 0 times -1 plus 1 times 1 plus 0 times 1, which is 1. So we very quickly have these key ingredients, and let's just substitute those in. A dotted with B is 1, magnitude of A is 1, magnitude of B is square root of 3. And what that tells us is cosine of this angle we are looking for is 1 over root 3, which note is not a common value, so we don't immediately look at this and just know what the angle is. But what we can do is write down something that represents the exact value of it. Theta would be the inverse cosine of 1 over root 3. And I would encourage you to leave your solution precisely in this form. If you plug it into your calculator and you get back a decimal approximation, it is exactly that. It's an approximation to the value of the angle. And this really finishes up the material that we are going to at least discuss together related to the dot product and the cross product. But as always, what this leaves us with is an opportunity to go through and practice examples. So remember, there's plenty of suggested problems, there's examples in the book, and we should not all feel the need to do every suggested problem, but instead what I typically recommend is that we should be doing enough to understand what's going on. And with that in mind, something that I typically do with my classes when we meet, face to face in person, is there'll be various times during the semester where we'll have, 25, 30 minutes at the end of class where I pass out a worksheet. I have you turn your desk, work with your neighbors, and kind of see what you can do. And typically by design, these worksheets will have maybe more problems than we'll necessarily get through in one given class period. But what I do is I'll post solutions on Canvas, and then I have you work through them as extra practice, and then check versus those solutions or let me know if you have questions. So with that in mind, if you look in Canvas underneath the videos associated with 12.4 in the cross product, you will find a link to first the worksheet, and then afterwards a link to a completed worksheet containing the full typed out solutions. And what I encourage you to do is to, look at this worksheet, maybe even set a timer if you need to, but give yourself, 25, 30, 40 minutes to kind of work through this and see what you can do. And after you do that, kind of come back to this video, and I'm going to go through two of the problems that are in the worksheet. I'm going to go through problem 1 and say something about problem number 4. So go ahead and pause the video, work through that worksheet, and then come back here and we'll discuss those solutions. Okay, so at this point, hopefully you've taken a few minutes to work through the worksheet. And what I'd like to do is discuss, to begin with, problem number 1, but I'm specifically going to just go ahead and sketch the associated vectors, and I really want to think about the projection vector because it has a small twist that we did not previously discuss. So let me kind of just remind you that the projection of B onto A is equal to A dotted with B over the magnitude of A multiplied by the unit vector in the direction of A. And in a moment, we'll go through the computations and kind of get those key ingredients. But let's first sketch a picture. So A is the vector 1, 2. So we go 1 in the x direction, 2 in the y direction. And B is the vector minus 4, positive 1. So we go 4 in that negative x direction, 1 in the positive y direction. And this may not be perfectly to scale, but hopefully it gives you an idea. To project B onto A, what we need to do is drop a perpendicular down from the terminal point of B to where it hits the vector A. So if I come down in the direction that would allow me to hit that vector at a perpendicular, note you don't really pass through the vector itself. What we need to do in this case is extend that vector A kind of in that negative direction, and we see where we will hit at a perpendicular. Then in this case, the vector going from the origin to that point of intersection, this would be the projection of B onto A. In terms of computations, I will let you work through the details, but A dotted with B is minus 2. The magnitude of A is the square root of 5. So you're going to have square root of 5 squared multiplied by the vector A. So 1, 2. And note, just so there's no confusion here, the square root of 5 squared is the magnitude of A, quantity squared. And if we put this all together, we'll have minus 2/5, which I'm going to leave out front because I think it's illustrative, times that vector A. And note, that's kind of what we're seeing, and I know the scale is kind of hard to judge, but we are not going specifically in the same direction as A. We're taking a vector that we've scaled, and we're going in the opposite direction. So the picture is really kind of illustrating what we see in the formula. Well, or maybe the formula is really illustrating what we see in the picture. Either way, it works. The other problem I wanted to say something about was problem number 4, I believe, where we are asked, you know, is the expression A dotted with B crossed with C meaningful? Which may seem like a strange question at first, but something that's going to be really important for us this semester is just really keeping track of the type of quantity we are working with. Is it a vector? Is it a scalar? Is it a function of one variables, a function of two variables? What types of things can we multiply together, etc. So let's just think about our quantities. C, not surprisingly with that arrow over it, is a vector. Whereas A dotted with B, the dot product of two vectors, excuse me, is a number. And there is no meaningful way for us to take a number crossed with a vector. For a cross product, you need to have a vector crossed with another vector. So the answer here would be no. And the reason to go along with this as to why we would say no is that a scalar cannot be crossed with a vector. And as I indicated a bit earlier, on Canvas you can find full solutions to the worksheet, and we will go through similar exercises many more times throughout this course. So I do strongly encourage you to kind of work through any remaining problems that you have, check versus the worksheet. If you have questions about the worksheet or anything really, reach out to me, drop me an email, stop by the virtual office hours. I would love to have a conversation. So everyone, take care and stay tuned.